Okay, so let's now get into a discussion of the Lewis structures of compounds. So, the Lewis structure, when we're talking about the Lewis structure of a compound as opposed to Lewis structures of atoms, what we're talking about is basically how the atoms in a molecule or a polyatomic ion is connected, how they are connected to each other, showing all the pairs of electrons involved. The point here is that the most stable arrangement is one where each atom ends up with a noble gas configuration. I would say that the most difficult part of writing a Lewis structure is determining basically how the atoms are arranged in the molecule or ion. And usually, if we're having a situation where we have molecules with more than one atom, or two, where more than two atoms actually, then one atom will be at the center, surrounded by the other atoms. So this begs the question: which atom will be at the center? And usually, it will be the single atom if there's only one atom of the particular element present in the molecule, or the least electronegative element. So, for example, if you take this molecule, Cl2O, right? There are two possible ways that these atoms could be bonded to each other. You could have them in series, as you can see there, where you have the chlorine in the middle and you have oxygens on either side, or you can have both chlorines bonded simultaneously to the oxygen. Question is which one would be the correct one. In this case, the oxygen would be in the middle, so this would be the correct structure because it is the single atom of that element present in this formula in this particular case. Um, that usually takes precedence. Otherwise, it would be the less electronegative element. Now, oxygen is not the less electronegative element in this case, so therefore that rule would not apply because oxygen would be the single atom in this formula right here. All right. So that's basically how you decide which atom goes in the middle. Now let's go into the procedures for writing Lewis structures. Couple of things you need to keep in mind. You need to know the number of valence electrons of the atoms involved. And you can pretty much tell, especially for the A group elements, which is our focus for this discussion, you can pretty much tell that what the group numbers are based on what the valence electrons numbers are based on the group numbers. So for example, chlorine is in group 7A, so it has 7 valence electrons. Nitrogen is in group 5A, so it has 5 valence electrons. Phosphorus is in group 5A, so it also has 5 valence electrons, and so on and so forth, right? So what I'm going to do, I think the best way to explain this is go directly into some examples. I'm going to skip some of this discussion here, and I'm just going to show you how I would work it out um, using the examples provided in this slide right here. So I'm going to open up a new um, slide right here. I'm going to take these out, and I'm going to go to the pen function. All right. And let me see if it works. Okay, it works. So the first example I'm going to use is water. So let me erase this first. Okay, so draw. Okay, so in the case of water, for which the formula, of course, is H2O, first thing I will do is count up the total number of valence electrons. So for hydrogen, it is 2 times 1, so that's equal to 2 electrons. And for oxygen, that would be, if you go to the periodic table, you'll see that the group number of oxygen is 6. So that's 6 electrons. So when you add these up, that gives a total of 8 electrons, right? So the oxygen being the single atom here would go in the middle, and it would be surrounded by the 2 hydrogens. And then I would start to put in the bonding pairs. You have 8 electrons here. So I'll put 1 pair here, 1 pair here, right? So we have used up 2 of the 8, or I should say 2 of the 4 pairs. Let me put 4 pairs here, right? Because 8 electrons is the same thing as 4 pairs of electrons. Now remember, each line here, I don't know if I made this point before, but each line here represents a pair of electrons, right? So therefore we have used 2 of the 4 pairs. So the question is, where will the other 2 pairs go? Well, you could not put the remaining pairs on the hydrogens because hydrogen can only have two electrons in its outer shell. So therefore, each hydrogen atom can only have one pair of electrons being shared or one bond being shared between itself and the oxygen in the middle. So therefore, that means that the remaining pairs of electrons will end up on the oxygen. So one pair would go here, and another pair of electrons will go on the oxygen. Another way of representing it is this: H, O, H, and you put a line here and a line here. So each line here and here represents a pair of electrons. And that's basically the Lewis structure of water. All right? So that's how we deal with water. Now, let me just jump to another example. In the case of carbon dioxide, so let me let me take out all of this, and let's look at the case of carbon dioxide. So in the case of CO2, whoops, why is this thing not writing? Hold on. Sorry about that. Okay, what's going on here? Okay. So in the case of carbon, okay, I don't know what's going on with this thing. It's not drawing for some reason. Okay, I don't know what's going on with this. Please forgive me. Or maybe I should do... Okay, wow, okay. So, in the case of carbon dioxide, we go to the periodic table, we look up carbon. Carbon has a group number of 4. Oxygen has a group number of 6. But there are 2 oxygens, so we have to multiply that by 2. So that gives us 12 electrons. So we add up the 4 electrons to the 12. That gives us 16 electrons, which is equal to 8 pairs. All right, so we have 8 pairs to assign. We put the carbon in the middle, surrounded with the oxygens. We put the bonding pairs, 1, 2, then 3, 4, 5, 6, 7, 8. Now, unfortunately, we can't stop here because even though the oxygens have their octet satisfied, each oxygen has 8 electrons, the carbon does not. The carbon has only 2, 4 electrons. So we need the carbon to end up with 8 electrons on its outer shell. And we can achieve that by pushing this pair of electrons here from this oxygen here to form another bond here. Same thing happens on the other side here. And therefore the final structure would be C double bond O, and that's it. And that would be the Lewis structure, because now this carbon would have 2, 4, 6, 8 electrons on its outermost shell. All right. Okay, so that's how we do carbon dioxide. Now, the next example I want us to look at has to do with complex structures where you have a polyatomic ion, such as the nitrate ion. Now, in the case of the nitrate ion, let me okay, I don't know what's going on here. Let me lasso all of this here. And delete. Go back to draw. Okay, so the example I want us to look at here is nitrate. NO3 minus. So we do as we did before. We go to the periodic table. We look up the group number for nitrogen, that is 5. We look up the group number for oxygen, that is 6, but there are 3 of them, so we multiply by 3. But now we have to take into account the fact that we have a negative charge. And basically, where for every negative charge that is present, we add 1 electron. So plus 1. Now 6 3 is 18, plus 1, 19, plus 5, that's 24 electrons, which is equal to 12 pairs. All right? We put the nitrogen in the middle, surrounded with the oxygens, 1, 2, 3. Then we put the bonding pairs, 4, 5, 6. Then we put pairs of electrons on the oxygens, 1, 2, 3. I'm sorry, 1, 2, 3 bonding pairs, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right? So, again, we have a situation here where the nitrogen does not have an octet, 2, 4, 6 electrons. So what do? We push a pair of electrons here to complete the octet for the nitrogen. So therefore the final structure would be N bonded to O, double bond to O, single bond to O. And in addition, we have to put everything in square parentheses and put a minus sign here to indicate that the entire structure carries a negative charge. All right, so that's basically how we do polyatomic ions. For every negative charge, we add an electron. And then also you can have a polyatomic ion with positive charges. So in those instances, for every positive charge, we minus an electron. In fact, let me do an example of that. So let me go back to here, lasso, let me take out all this again. And let me go back to the pen function. Okay, so the example I'm going to look at now is ammonium. All right, so we go to the periodic table, we look up nitrogen, that gives you 5. We look up hydrogen, that gives you 1, but we have to multiply by 4. So that's going to be equal to 4. And then the positive charge, for that we subtract an electron. So therefore the total number of electrons we have to assign is 8, which is equal to 4 pairs. We put the nitrogen in the middle. We surround it with the hydrogens. And then we put the bonding pairs 1, 2, 3, 4. And then, of course, we have to put this in square parentheses and then put the plus charge outside. Now, in this case, the nitrogen has its octet satisfied, so therefore we don't need to make any further changes to this structure. Okay, so that's basically how you will determine the Lewis structure for a molecule or ion. All right, let's see what's next. So let me jump all of this here because I've covered all this a while ago. I also covered that. Okay, so what I'm going to do is stop here, and the next video will deal with molecular shapes. So until next time.